Okay, we are continuing with our previous exploration of the previous interpretation of the paper. We are now discussing section 3.7, reconstruction of the diffeomorphism group for null hypersurface in Schwarzschild spacetime. So the main theme of this section is that we find singularities along the null hypersurface of we find singularities in the metric along the null hypersurface. So we do not, and also because there is no diffeomorphism symmetry, we do not employ Einstein equation or the analytically extending the metric along the null hypersurface. Instead, we use the Raychaudhuri equation. If we label the null hypersurface as eta and use the information eta transpose eta is equal to 0, we will not assume any other information about this null hypersurface, but for a 4-vector chi along time-like region, owing to consistencies from experiments, we assume that coordinate chart chi in time-like region follows Raychaudhuri equation and geodesic equations. Raychaudhuri equation in a generic 4-dimensional spacetime is this: d theta by d tau is minus theta square by 3 minus sigma square plus omega square minus r mu nu xi mu xi nu. Xi mu are the killing vector fields, theta is the expansion parameter, sigma is the shear, and omega is the vorticity or the deviation from rotational flow, and xi alpha is the derivative of xi alpha with along alpha is the derivative of killing vector field along the tangential component of the covariant derivative. One might question if Einstein equations are valid near black hole horizon given that the diffeomorphism symmetry is absent. It was suggested in a paper that Raychaudhuri equation can be derived independently as a geometrical flow equation. A geometrical flow in some sense is like the interpretation using fluid gravity correspondence. So in symplectic geometry, we consider flows along in a manifold, and I do not have much information about it. And given that Raychaudhuri equation can be derived as a geometrical flow equation, we presume that Raychaudhuri equation are more fundamental and are valid when there is an absence of diffeomorphism symmetry in black hole spacetime. However, we are still not done because this equation doesn't assume a superspace structure to Einstein gravity. Superspace structure is essential because we have already reviewed this in previous video, and alongside we have Finsler geometries which suggest non-commutative nature of spacetime. We will not tackle the problem in its full generality, but we'll see that we can derive interesting properties despite not considering these other foundational issues in our paper. We assume validity of Raychaudhuri equation along time-like region tau and along null hypersurface sigma, and that the two regions are related by equation 3.1. Eta is equal to d chi. However, we do not have an explicit form for shear in the same paper. It is suggested that the shear potential in its equation 6 in the paper has an explicit dependence on the volume of the cross-sectional surface. Our motive is to derive the explicit form of the coordinate chart along null hypersurface using Raychaudhuri equation along time-like and null hypersurface. So what we'll do is to use the Rai-Chaudhuri equation along time-like region and null region. Null region we find is a very complicated business because it has many other associated degrees of freedom, associated fermionic degrees of freedom that come in the picture when we study, when we are trying to study congruences or in computing geometrical quantities like area volume or the area volume or entropy. However, we will not worry about these conditions here. We also have an extra condition of zero norm of null hypersurface, but we do not presume geodesic equation for null hypersurface coordinates. In most scenarios, Rai-Chaudhuri equation is derived using derivative of velocity vector field as in equation 1 of 2. We do not know how to make an equivalence. We do not know how to make an equivalence between Rai-Chaudhuri equation using geometrical flow and deriving it using the approach of 2. So derivative of velocity vector field essentially means this. Just a minute. Yeah. Theta prime is the derivative of the area. Theta prime is the expansion along null hypersurface and theta is the derivative along the time-like region. We haven't been able to derive these equations, but these equations have been suggested in section 2.4.8 of book by Professor Eric Poisson, Relativistic Toolkit. Just a minute. Okay. Now, as suggested in the same paper after equation 14, Rai-Chaudhuri equations are Rai-Chaudhuri equations are identities and not equations, and therefore are valid even when Einstein equations, owing to absence of diffeomorphism symmetry, might themselves may not necessarily be valid. For notational simplicity, we rewrite these identities suggested in the paper. So 3.43 is the same equation. 3.44 is the equation for the shear. The last term is R tilde AB, not RAB. And this is the equation for the vorticity. Sigma AB is a symmetric tensor. Sigma square is the norm square of sigma AB, and omega square is norm square of omega AB. CABCD is the Weil tensor, and R tilde AB is this, as suggested in equation 3.46. HAC is the projection tensor. So HAC when dotted with UA or UC gives 0. So it's a tensor which is orthogonal to the velocity vector field. So its components are orthogonal to the velocity vector field, or it's a second rank tensor which is normal to the velocity vector field, to the hypersurface along which we are considering the metric functional and the velocity vector field. UA is normalized to 1. One may question how to find the... Okay, so in these equations, we know all the parameters in 3.43, 3.44. and 3.45 as a coupled set of differential equations. However, we have HAC is depends on the velocity vector field UA, and to find UA we need to solve for the four set of coupled differential equations or the geodesic equations. For Schwarzschild spacetime, the four set of coupled differential equations are these: 3.48, 3.49, 3.50, 3.51. Please note that we do not assume any spherical symmetry here, and UA is equal to dxa by d tau is the tangent. UA is then dxa by d tau. So solving for t rho theta phi, we can find UA. Interestingly, we asked ChatGPT to find the solution to these four set of equations, and it gave us the following solution. UT is this, UR is 3.52, 3.53, 3.54 and 3.55 are the four set of equations for the four velocity vector fields. Similarly, for the null hypersurface, the authors in 2 suggest in equation 17 the Raychaudhuri equation. So theta prime is the expansion along the null hypersurface. Sigma prime and omega prime are the shear and vorticity along the null hypersurface, and RAB is the Ricci tensor along the null hypersurface. Ka and Kb are the null velocity vector field. Please note that in equation 3.56, right hand side carries only symmetric terms and its indices. So even if we assume metric to be asymmetric, so metric, we do not presume that the metric along null hypersurface or the diffeomorphism symmetry group as found earlier needs to be symmetric, but the right hand side in this equation is symmetric. Even if the Ricci tensor RAB is not symmetric, KB is a symmetric term, so it cancels the anti-symmetric part of RAB. So the left hand side should also be symmetric. Just a minute, please. Just a minute. Okay, so primed quantities are expansion, rotation, and shear for the null geodesic congruence. Like equation 3.24 and 3.25, we have analogous equation for sigma prime and omega prime as tensorial equations. These are 3.57 and 3.58. So these equations are the shear and vorticity along the null hypersurface. We have we have discussed the interpretation of expansion. However, we do not yet know a way to find area and volume V. However, suppose we consider a foliation of Cauchy slice. Just at the instant a black hole is formed, we know using the language of differential forms that V is this. V is the inner product of the four set of time-like coordinates along with the scaling factor root det g. Assuming foliation is along one of the coordinates say chi4, we have V is this. Here the integration needs to be done over the time-like region along the black hole spacetime outside the null hypersurface. Okay, so assuming foliation is along one of the coordinates, we have V is this. Here the integration needs to be done over the time-like region along the black hole spacetime outside the null hypersurface. Similarly, in that slice, we have, okay, just a minute. V is this, and foliation means that we are taking a projection of the manifold along one of the coordinates, and how this foliation is done is another question, but given the volume along the time-like region, we can consider a sub manifold along the foliated slice. That foliation is along the null coordinates, and we can find the area as integral over the null hypersurface along the foliated slice. A is integral along the null hypersurface scaled with induced metric determinant det h d eta 1 d eta 1 wedge d eta 2 wedge d eta 3. Again, we have to integrate the null hypersurface region sigma along with the condition eta transpose eta is 0. Assuming such a foliation can be done so as to eliminate one of the coordinate of eta, we have two parameters for integration of A. However, whether we can, okay, ये क्या है यार? However, whether we can do such a foliation is another question. So the area is a two-dimensional hypersurface, which makes the analysis of the induced metric in 2 dimensions much simpler. But we will not assume that null hypersurface metric is diagonal or symmetric in its indices. Hence, there are 4 components for the metric. Also, because the spacetime outside the black hole horizon satisfies vacuum Einstein equations, so we have R mu is 0 for such a Cauchy slice. So R mu, the Ricci tensor along the time-like slice, is 0. However, we notice immediately that we have presumed an infinitesimal ball-shaped region hugging both the time-like region tau and the null hypersurface region sigma. This is presumed to happen along some Cauchy slice containing both the regions. But as we start foliating such Cauchy slice, we'll find that there is a blue shift in the future, so that the blue shift and the gray body factor will back react at late times, distorting our construction to reconstruct null hypersurface. It is also questionable if such diffeomorphism even exists or not. As in section 3.4 and in equation 3.21, we found that the diffeomorphism group could have been 0 also. However, we found that in equation 3.21, we found the diffeomorphism symmetry group. Yeah, so this was the diffeomorphism symmetry group, and it was non-zero. Okay, this is we also need to know the induced metric determinants G and H. Hopefully, we know the metric along time-like region tau as Schwarzschild metric owing to experimental observations. Oh, I can't. However, we cannot say so for the null region. So we can proceed to link the set of equations derived in section 3.7 of the paper with coordinate chart with coordinate charts along time-like region and null hypersurface, and then link them using 3.1. This will be helpful. This will help us to find the null hypersurface modulo one more condition set of conditions. We assume the condition is smooth variation of coordinates as we move along a neighboring region from time-like surface to null hypersurface. This can be stated as the condition that the time-like 4 vector motivated in equation 3.1 chi as displayed along a neighboring region along sigma is same as eta. Okay, we have an epsilon ball shaped region which is hugging both the null hypersurface and the time-like region, and as we are drifting from the time-like region to the null hypersurface, we assume smooth variation of coordinates. So chi is the time-like vector field, and as it progresses towards sigma, we assume that it's equal to eta, or it means that as the radius of the diffeomorphism group approaches 0, the matrix D in equation 3.1 becomes identical to identity. So equation 3.63 means that eta is equal to chi along sigma. So the diffeomorphism group is identity because eta is d chi. For small deformations, we assume the diffeomorphism group can be expanded via its set of generator close to identity. This will provide us the algebra of the diffeomorphism symmetry group. Hopefully the set of equations from 3.43 to 3.62 can be assumed to be sufficiently able to develop the coordinate chart for smoothly reconstructing the null hypersurface of black hole spacetime. Until now, we have only supplied geometrical identities and not an equation. We attempt to provide a consistently complete set of solutions by providing few more set of equations known as Gauss-Kodazi equation and Israel junction condition as suggested in chapter 3 of Eric Poisson, which ensures smoothness of horizon, but it seems like we do not, but we will require these equations. These equations can be taken directly from Eric Poisson textbook, but we'll comment about it later. Because a null hypersurface has zero norm, a manifold with an oriented normal along time-like region needs to change its sign necessarily. Because a so null hypersurface has both tangent and normal vectors along the same direction. This is a peculiar property of null hypersurface. So this means that the normal which is orthogonal to the time-like region, as it proceeds along the null region, it should become tangential to the tangent vector field, so it must change its sign. In the language of fiber bundles, this means that if fibers of some base manifold which admits a suitable foliation necessarily travels back in time as it passes from time-like hypersurface to null hypersurface. So what I will explain this more precisely. So what are fiber bundles? Suppose you have a hypersurface or a Cauchy slice. You call this Cauchy slice the base manifold, and you have rays or fibers projecting orthogonal to the base manifold. So these this can be, so you can assume that given a base manifold, the evolution equation of the base manifold with time given such a foliation can be described using its fiber data. So fibers are essentially useful to describe the evolution, and the topology of the manifold of n plus 1 dimension can be written as locally as tensor product of a base manifold which is n dimensional times the fibers. Fibers can have certain kind of symmetry associated with them, like if the fibers vary smoothly and are always unidirectional, they are, the topology of the fiber can be R, the real line interval. If the fibers are curling like a helix, then the topology of the fiber can be assumed to be SON, where n is the dimensionality of the fibers. So what we are essentially assuming is that we have a manifold. It can be foliated into a base manifold times tensor product with fibers. Now you can examine this situation for Schwarzschild spacetime. Suppose you have foliated the Schwarzschild spacetime into a base manifold times its fibers. Then the fiber, if you assume the fiber is like the time direction, which describes the evolution equation of the base manifold, then the fibers are moving upwards along the time-like region, but along the null direction, since the time coordinate switches sign with spatial coordinate, the base manifold has undergone some kind of twist, a twist like that in the Mobius strip. So instead of propagating forward in time, the fibers are now bent in the opposite direction. If we assume that this spacetime manifold is smooth, this means that the manifold along the null hypersurface is traveling back in time. However, proving this statement rigorously requires deep theorems and results from Riemannian geometry and differential geometry, but certainly this process does not seem to indicate more subtle effects like topology change, which is captured using DRAM cohomology. Okay, so proving this statement requires deep results from Riemannian geometry and differential geometry, but as long as the base manifold is smooth, we can certainly say that the topology of the spacetime manifold is still smooth. It can be a metric topology or a differential topology, but so we considered the example of the donut. So the genus of the manifold or the topology of the manifold is still the same. And to capture these topological effects, we need DRAM cohomology. However, just to make some progress, we now attempt to solve set of equations from 3.43 to 3.62 using an assumption in equation 3.61 and 3.62 that the change in expansion is carried only as a function of metric, so that while taking the derivative of volume V and area A, the change is carried only as a function of metric. In particular, we use these two more set of equations that simplify 3.59 and 3.62 to this. So what we essentially saying is that V is this root det G d chi1 wedge d chi2 wedge d chi3, and A is this. Now theta is the fractional rate of derivative of volume with the affine parameter tau, and theta prime with affine is the fractional rate of change of area with affine parameter lambda. Now if you supplement A is this 3.62, you will encounter terms with derivative of d eta 1 by d lambda upon d eta 1 and so on. What we presume is that these null coordinates as a first order approximation can be assumed to not vary with lambda. The change in the first order approximation is only with reference to the induced metric root det H. Now if you use this equation, you find that theta prime is this 3.64 and theta is 3.65. Now for simplicity we write then okay, so we have assumed a foliation of the null metric, and along the foliated slice we are assuming along the foliated slice the metric induced metric is two-dimensional, so H mu nu can be written in this manner. Similarly, the inverse metric has this form. In two dimensions we find theta prime is this, so we simplify theta prime and we find it is equal to 1 by 2 det H d by d lambda det H, or using 3.68 says that theta prime is 1 by 2 d by d lambda ln of det H. Also in two dimensions, in presence of asymmetry of metric or torsion, we have the expression only for symmetric indices, here owing to symmetry to the right hand side of equation 3.56. Okay, so the left hand side should be symmetric in the indices. However, we'll work in a way that we do not require indices. We will work in a tensorial way, as we will see. Also in 2D, the expression simplifies to R mu nu is R by 2 H mu nu. This is true in two dimensions. This is an important geometrical identity which is necessary for simplifying our answer, and assuming how to proceed without assuming such a foliation of 2D slice is a difficult question that we tried to solve, but we couldn't proceed in its entirety. Asymmetric metric implies an asymmetric line element, which indicates that if a tensor analysis for line element is valid, then the event horizon has non-commutative nature, though we do not claim it here because we do not assume that metric always is a fundamental arena for taking inner product for computing the line element. What we are saying is that we do not assume ds square is g mu nu dx mu dx nu. As we have provoked, we do not assume that metric can be used for scaling coordinates for taking inner product. So we cannot assume the same for the line element. We assume ds square is dx mu inner product dx upper mu, but we do not use the g mu for scaling them. Instead, since they are co-vectors, how we proceed is by taking the inverse of dx mu. So dx mu is a 4-column vector, dx upper mu is the transpose of that with suitable sign. It is only in Minkowski spacetime we presume it is true. Also in equation 3.56, Ka is dxa by d lambda. Yeah, so we had Rab Ka Kb. We'll review equation 3.56. Rab Ka Kb. So Ka is the tangent vector along the null direction, so it is dxa by d lambda. Where xa are coordinates on the null hypersurface. Thus equation 3.56 simplifies to 3.70. Here we, in the right hand side, we have used Rab is r by 2 Hab Ka Kb. In where theta prime is as suggested in equation 3.68, theta prime is the fractional rate of change of the area. In 2 and 3 dimensions, we have another simplification. The wild tensor vanishes, so equation 3.58 becomes d sigma prime ab is this. We can write equation 3.71 as d by d lambda ln sigma prime ab is minus theta, and d omega prime ab by d lambda is minus theta omega prime ab. To proceed further, we use bit of tensor analysis. We multiply equation 3.71 by sigma prime ab. So we find sigma prime ab d sigma prime ab by d lambda is minus theta sigma prime ab, which is minus theta sigma prime square. This can be written like this. So sigma prime ab d sigma prime ab by d lambda is d sigma prime square by d lambda plus theta sigma prime square. Multiplying above equation by sigma prime ab, we find d sigma prime ab by d lambda sigma prime ab theta times theta plus 1 by sigma prime square d sigma prime square by d lambda. Equation 3.74 can be written like this, 3.75. From 3.75 and 3.73, we see triviality relation for sigma. Triviality relation means that just a minute, I'm coming.